signal will go directly to straight forward, otherwise it will add into the system. So this is how we can actually use MEMS to add and drop signal into the networks. And this is an example of optomechanical switches because we are using the lenses, and lens has got a fixed life, so they are not that reliable as the non-mechanical switches are, because the movement and the rotation method on the process will always affect the performance of these switches. Advantage of these switches are they have got low insertion losses, low polarization dependent losses, but the disadvantage are lack of scalability. We cannot design higher order switches. This is an example of 4x4. You can see the 4 inputs and 4 outputs. So this is an example of 4x4. But if I want to design a 100x100 MEMS switch, that will be quite difficult for me, because I need to have more and more lenses, and I need to have a rotational algorithm with how to rotate all those lenses simultaneously. Then electro-optic switches, these are purely based on the material properties. Like we have an example of an electro-optic switches. What we are doing, we are just having 2 small waveguides made up of some particular material which has got a good electro-optic coefficients, and when the signal comes from this branch, it can either come across the output 1 or output 2 depending upon the refractive index of these branches. If you know if you are aware of the fundamentals of the optics, the light will traverse where the refractive index is more, in the core, right? So if I using the electrode configuration across these 2 branches, if we can make the refractive index of this upper branch more than this, the light will travel from this and will goes to the output 1. But if we can change the configuration of the electrode again, and if we can make the refractive index more in the lower branch, the light will goes into the and will connect with the output 2. That means the switch will work in cross state. Earlier it was working in bar state. So this is how we actually get the switching across the electro-optic switches, just by playing with the refractive index properties of the material. And how we are changing the refractive index? We are just changing the refractive index by changing the polarity across these 2 closer waveguides. And this is how the electro-optic switches works. However, the disadvantage with them are they have got higher insertion loss and possible polarization dependence and higher driving voltage. That means since we are using the electrode across these 2 closer waveguides, we need driving voltage also. But at the moment we require higher driving voltage to achieve this kind of switching. Similarly, thermo-optic switches. So in thermo-optic switches, switching is performed by variation of the refractive index of a dielectric material due to the temperature variation of the material itself. But just by changing the refractive index of the material with the effect of the thermal or temperature variation, we can actually achieve the switching in these kind of switches. They are generally small in sizes and high driving power characteristics. However, the problem with them is they have got limited integration density and high power dissipation. We cannot come up with the large port count of such kind of switches, because in that case there will be difficult to variate the temperature at some particular points. Similarly, they require forced air cooling for reliable operation. Since we are playing with the temperature, environmental temperature across these switches, so we need to also apply forced air cooling for their reliable means, for their operation for a longer period. Then there are more other switches, liquid crystal switches. There are certain material in which their crystalline forms comes into the liquid, and after some time they become solid, and this is how we achieve the switching. Similarly, acousto-optic switches. So I'll just make a comparison amongst these categories of switches. In optomechanical switches, the scheme says we employ electromechanical actuator to redirect a light beam, and these electromagnetic actuators are basically lenses. They just redirect the light beams. Strengths are, these are very good in optical performance. However, this is a old technology. Weakness, speed, slow, bulky, and the scalability is again a weakness for them. Potential application, we can use them for protection switching, because for any network we require very low port count protection switch, so we can actually employ them in the protection switching application only. Optical add-drop multiplexing and OSM, optical switching matrix. Then MEMS, they use tiny reflective surfaces. Strength are size and the scalability. However, the weakness is packaging and reliability. They can use OXCs, means optical cross connects, to design OADMs and OSMs. Thermo-optical, the scheme is temperature control to change the refractive index. Strength is integration, wafer level manufacturability is possible. The weakness is optical performance, power consumptions, speed, and then scalability. Their potential application is optical cross connects and optical add drops multiplexing. Moreover, all the switches can be used for optical add drop multiplexing. This is a very common application for all sort of switches. Then liquid crystal, gel and oil based, and magneto-optics also. Now the question is, once we design a small switch, means 1 cross 2, means one output, one input and 2 output, or a 2 cross 2, 2 input and 2 output. Can we go for a large architecture? Because these are the only small port count switch. Now we need a higher port count switch. Like if the inputs are 1034 and the outputs are 1034. So how to design the large architectures? So there are specific. But once we go for the large architecture design, switching architecture design, we need to check. These are the constraints, these are the points which we need to check before designing a large architectures. First is crosstalks. Any single switch has got some sort of crosstalks, and if we want to design a large architecture, their crosstalks will be multiplied. Similarly, path delay, how much delay will be there? Because if we will have a large number of input and output port, can we connect all the input to all the output, and what would be the path delay? Coupling power losses, when we will be coupling power from one port to the other port, or to many other ports, then there will be coupling losses will also be there. So we need to tackle those losses also. Blocking features, blocking and non-blocking switches are, if we can connect all the input and all the output, that means if we can have the combination of all input output connecting patterns, then the switch is non-blocking. So we need to take care of this also. If we are going for a large architecture design, should we have the blocking feature or should we have the non-blocking feature? Rearrangeability. Can we use some sort of algorithm to rearrange or to rename our input and output ports? And on-chip viability means, since we are going to work with the VLSI technology also, so we need to design the switches in terms of their compatibility with the on-chip systems. So this is an example of designing a large architecture. You can see it has got 16 small 2x2 switches, but using this architecture we are actually designing a 4x4 switch, but it is using 16 2x2 switches. So once we design a principal element 2x2, and by connecting these 16 elements in this fashion, which is known as crossbar architecture, we can actually come up with a 4x4. But you can see this is a wide sense non-blocking, means we can connect all the inputs to all the outputs. I can connect 1 to all outputs, 1, 2 or 3 or 4. Similarly, 2 can be connected with all the outputs, 1, 2, 3, 4. All input output pattern are possible. However, the n cross n switch requirement is n square. If using this architecture, using this design, if I am making a 4x4 switch, how many switches I am needing? 16, 4 square. Similarly, if we go for 8x8, then 8 square, that means 64. So number of principal or basic elementary switch are more in this architecture. Shortest path length is n, means it is a example of 4x4. If I am connecting 1 to 1, so I need to cross at least 4 switch. So this is the shortest path length. Similarly, longest path length is 2n minus 1. In this case, n is 4, so longest path length would be 7. That means to connect 1 to 4, I would need to cross at least 7 basic switches. So as many as switch we need to cross, that means we are going to face the losses, the crosstalks, and the delay also. So these are the important points which we need to take care of when we go for the higher order design. Similarly, bad loss uniformity. Loss uniformity is, okay, I can consider there will be a loss when I'll connect one input to other output. But at least for all the possible input output connecting patterns, the losses should remain same. If I am connecting one input 1 to output 4, there will be some loss. And again, if I am connecting 1 to output port 3, there will be another some loss. but these two loss should be the same at least. That means if I am having a loss in this switching system, there must be a uniformity in the losses for all the possible input-output connecting pattern. The losses should remain same. If the losses are, if there is a variation in the losses, that means that there will be another problem for me to tackle with the issues. And another good thing with this architecture is fabricated without any crossover. Means all the connecting wires are not crossing each other, so they are separated. So whenever there will be a crossovers, we need to do the stacking parallel. So in that case, the circuit will be complex and bulky, and the size will also be more. But for this particular architecture, we don't require any crossover. So this is a good thing. The bad thing with this is bad loss uniformity. There is no uniformity in the losses. Similarly, switch requirement is another bad thing with this, because we required n square switches. So can we go for another design? Yes, Spanke architecture. This is an example of n cross n switch, and given by the Spanke, so the name is given as Spanke architecture, and it is also strict sense non-blocking. It requires only 2 stages, where we design 1 cross n and n cross n switches instead of 2 cross 2. Switch cost scales linearly with n. How many of number of elementary switch we would be using, the cost will be increasing in this. The lower insertion loss, it has got equal optical path length. With this kind of structure, the optical path length will be the same, but you can see this requires the crossovers. The connecting wires are crossing each other, so we need to have the stacking of the elementary switches. Then there is another Benes architecture. This is an example of 8 cross 8. So earlier, if we would have used the crossbar architecture, so to design a 8 cross 8, we would have required around 64 switches. But in this architecture, we are designing a 8 cross 8 switch, and how many switches we are using? Only 20, right? So this is a rearrangeable non-blocking. N cross n Benes switch require this much of switches. Means it's basic switch requirements in Benes architecture are very less than the crossbar architectures. Efficient in number of 2 cross 2 couplings. Then the network depth is 2 log 1, and it requires waveguide crossovers. But in this architecture, you can see there are the interconnecting wires which are crossing to each other. So we need to have the stacking again. So this is the disadvantage with this Benes architecture. So can we come up with a combination of 2 architectures? Like we can use the good thing of Benes architecture and advantage of Spanke architecture, and can we come up with a different architecture covering the advantage of both of these 2 architectures? Yes, we can. Spanke-Benes architecture. Now you can see we are designing a 8 cross 8. However, the number of switches are little higher than the Benes architecture. Earlier in the Benes architecture, for 8 cross 8 we were requiring 20 switches only, but now we require around 28 for 8 cross 8. But good thing is with this, we don't have any waveguide crossover. Here we were having the waveguide crossovers, but with this, the combination of Spanke and Benes architecture, we can actually avoid the crossover, waveguide crossover. So whenever we go for the higher order switching design, we actually need to take care of the trade-off between the various performance parameters. It depends upon the application, what sort of application we are going to place our switch into which application. So according to that application, we need to take care of whether we can avoid the waveguide crossovers, whether we can avoid the crosstalks, whether we can avoid the coupling losses, whether we can avoid the number of switches, whether we are concerned or serious about the size or the cost. So according to that only, according to these criteria, we need to choose our architecture to design the higher order switching matrix. This is another popular architecture, Banyan architecture. Here you can see the 16 cross 16 switch can be designed with as much as low number of basic switches, and this is self-routing capability. This has got self-routing capability, small depth, only log n with weights 2, low loss and low attenuation. And one of the good thing with this Banyan architecture, it has got the absolute loss uniformity. That means the losses in all possible input-output connecting patterns would remain the same, and that is why this is more popular as compared to the other architectures. A few of the designs examples I would like to share with you, which we have done in our lab. MZI structure, that is Mach-Zehnder interferometric structures. So this structure is very popular to design all optical switches. and it works. The principle of working of this structure is it has got two coupler connected with the interferometric arms. The first coupler is used to divide the power into two equal part, and these two power propagate through the interferometric arms, and using the combination of the electrodes we can get this switching, and the entire power can get connected, be added again with the second stage 3 dB coupler. So in the first case, this 3 dB coupler is known as the splitter because it split the power into two parts. The other 3 dB coupler is known as the adder because it is going to add these two powers, and we can have the power at any other points, whether it's the output 1 or output 2. If the power is coming from input 1 and if we can get it out from the output 1, that means the switch is working in the bar state, and if the power is coming from out 2, that means the switch is working in the cross state. Now how we will get the power from out 1 or out 2 will depend upon the position of the electrodes, and here we are going to use the electro-optic effect. So this is the example of Mach-Zehnder switch. A sort of history about this, why this structure is being used to design all optical switches. It has got the performance stability. These were the authors. They have done a very good work and they have come up with some good outcomes about this structure in 1986. What they have done, they have designed the Mach-Zehnder interferometric optical switch, and then they have checked its performance for a range of power and for a range of over the period of time. And what they found, even if this switch works from 1 watt to 10 to the power minus 6 watt, for this range of power, its performance parameters like extension ratio, total phase change, insertion losses and switching voltage remains constant. Similarly, if we can operate this MZI modulator for over a period of time, these parameters remains constant, means they are not varying. So this is a very good structure as far as the performance stability is concerned, because once we design the switching, because a single switch is actually capable of handling the entire network, similarly is also capable of destroying the entire network. So we need a switch which can perform stably, which has got the stable performance. So this structure has proven to be the stable in terms of the performance. Now how do we do the research in terms of the designing? Just by changing a sort of design, we can actually come up with a new performance parameter. Like the same MZI structure is being used here. Now these authors somewhere from China, they have come up in 1997 with the outcomes. If in place of using the symmetric 3 dB coupler, they have used the asymmetric Y junction. So here you can see the width of the waveguides or the upper and the lower branch are different, and they have just made these changes and they have come up with some sort of good results. They have shown that this switch can be worked with the switching voltage of 15 volt, while the branching angle were kept as 0.1 to 0.4 degree, and however they have evaluated this switch for TM polarized light only. They haven't given the results for the TE lights, and the crosstalk levels were calculated in between somewhere around -27 to -22 dB, while the insertion losses were also be in and around 2 dB. And they have drawn the graph for both states, cross states and the bar states. So this is how the we have the performance criteria with respect to the flexibility in the design. If we just change a sort of design, we can actually come up with a different kind of performance for the same structure. Like another group of authors from China, they have come up with another good result in 2010, and they have published a paper with this also, and they have again used the same structure, MZI structure. However, in place of first 3 dB coupler and the second 3 dB coupler, they have used the directional coupler with a sort of delay, which is known as phase generating couplers. So they have come up with the title polymer based MZI electro-optical switch using two phase generating couplers. In this case, what they have done, they have not used this similar propagation length in the couplers. They have put sort of delay over here, and by doing so they were able to achieve the electro-optical region length of around 5 millimeter with this, the switch was working for the spectrum around 1380 to 1730 nanometer. That means many applications it can accommodate. Switching voltage requirement is very, very less, plus minus 0.925, while the earlier design was actually requiring 15 volt, and now this design is requires only 0.925 volt at the wavelength of 1.55, and the crosstalk is also good, minus 30 dB, while the earlier one was having maximum of minus 27. So this is another good example. Then a student from a Malaysian university, he did his master's thesis in this particular topic only, and he designed the MZI switch using the different material. Now earlier the researchers were playing with the design of the structures. Now some of the researchers are playing with the material. They are keep on changing the material of which this structure being made. So he has used the titanium lithium niobate and he has come up with the design, and for this particular switch the switching voltage requirement was 12 volt, which is again high. However, he has shown that the change of wavelength is directly proportional to the switching voltage. This line he has actually come up with a new innovation. So I would rather suggest, since most of you are from the electronics and most of you are working with the antenna or the VLSI design, however all the fields in the electronics, these are correlated. Even if you are working with the antenna, you can maybe in the coming time you can come up with the optical antenna. If you are working with the VLSI circuit, you maybe come up with the photonic integrated circuits. Means all the components which you are going to place in the VLSI chip will be working in the photonic domain. So we have got already the photonic integrated circuits that is correlated with the VLSI, and similarly the optical antenna that is correlated to your antenna engineering. So when you go for design of MZI switch, these are the important things which we need to take care of. First is length of the interferometric arms. What should be the length? What should be the appropriate length we should choose if we are designing a MZI? What should be the coupling area of the constituent 3 dB coupler? Similarly, unequal interferometric arm and shape optimization. Can we have the equal interferometric arms for all the times, or can we have the unequal interferometric arms? Then the effect of changes in electrode dimension. Since we are going to work with the electro-optic switch, so therefore we would be requiring the electrode combinations also. So can we have the changes in the electrode dimensions? Similarly, the control sensitivity. What are the parameters? It is more sensitive to control. Then control voltage range. Equivalence in switching performance in different states needs to consider. Now I would like to share some of the results which our student had performed. Like they have designed a very symmetric and a simple MZI switch. They have defined all the parameters. What would be the length, what would be the width, what would be the interferometric arms, what would be the angle, which band they have used. They have used the S band to connect the 3 dB coupler and the interferometric arm with some sort of results. They have compared these results with the previously published papers and found all the results almost same. And the different thing which they have come up with, the calculation of the power imbalance of first stage 3 dB couplers. See, in a MZI structures, this 3 dB coupler is used as a power divider, because it is going to, or a power splitter, it is going to split this power into two equal parts. But when these two equal part power, that is P1 propagate through the interferometric arms, at these 2 points actually they becomes Q1 and Q2 because of this some sort of the losses. So they have calculated the relation between these two powers Q1 and Q2 and the earlier powers P1 and P2, and then they have checked the effect of these power variation on the performance of the crosstalk of this switch. And this is and their switch was actually working with the requirement of the switching voltage of around 7.3, but the new thing was that they have come up with the effect of the power imbalance in the interferometric arms with respect to the performance of the switch. And they have designed this switch with use of titanium indiffused lithium niobate substrate, and they have done it with the buffer layer, without buffer layer. Buffer layer means placing a layer in between the interferometric arms and the electrode to save the switch from the higher electric fields. effect of the higher electric field. So sometimes we use the buffer layer also, but in that case the switching voltage requirement goes little high. Similarly, they have come up, then this Ti in diffuse lithium niobate, it also work in two different crystal cut orientation, with two different crystal cut orientation, whether it is an X cut or the Z cut, that also they have done. Then another switch also they have evaluated, that is SOA MZI switch, which is a semiconductor optical amplifier in which they have inserted a MZI structure, and they have performed within the MZI structure they have inserted a SOA, which is semiconductor optical amplifier. As the name suggests, it is used to amplify the optical power. So whenever we lose some sort of optical power in the interferometric arms, we can actually use the SOAs to regenerate that power, and we can actually enhance the performance of the MZI switch. And they have evaluated sort of parameters and plotted. Thank you very much for this presentation. Now I would like to skip for the second presentation. Popularly used by researchers and the scientists to come up with the all optical switching or the coupling design. The other one is multi-mode interference based optical switches and the couplers. These structures has got unique properties. They are very much compact in nature, relaxed fabrication tolerance, large optical bandwidth, and the polarization insensitive. They have been preferred to design couplers, splitters, multiplexers, switches, and their work principle is by eliminating optical confinement to change the waveguide behavior, or by altering the imaging length by changing in the refractive index. So moreover, whenever we talk about the electro-optic or the thermo-optic switches, whether they have been designed with the MZI structures or the MMI structures or with the bi-junction structures, we actually change the refractive index with use of some sort of the effect. So this is in the history, I will not go into this. This is how in multi-mode interference structures, when power enters from one port, it actually, after traveling a specific propagating length, it divides into two equal paths, and again after traveling with specific propagation length, it actually combines and goes on to the other port, and again it divides into two equal parts, and so on it propagates through the coupling length. And if by selecting the coupling length, we can always make it as a switch. Let's see, if the power is combining at this port, if I can get the coupling length of only this, then I can get the power at this port. That means power is entering from the lower port and I am getting the power from the outer port. That means we can get the switching in cross connection. Similarly, we can get the switching in the next stage. This power will comes here. So here we can get the switch in the operating in the bar state. This is how we work with the multi-mode interference switch. And many of the previous researchers have come up, have used this structure, and they have come up with a different kind of configuration. Like they have come up with 1x2 MMI switch with butterfly configuration, in which they have used the coupling. This is known as the coupling length, where the most of the power will actually decide which port it will go. So they have used, in place of the symmetric coupling length, they have used the butterfly connections. Take the design of a butterfly, and they have used the material indium gallium arsenic or the indium phosphide. And however, with this design, losses were less. However, the PDL were not, because the PDL is propagation dependent loss, as the provision for W0 and W1 is taken different for TE and TM polarization, which makes fabrication process tough. And this work was done and was published with the Journal of Light Wave Technologies in 1996. Then MMI coupler based modulator and switches with the electro-optic effect. They have simple this BMA Rahman from somewhere from the UK university. They have submitted they have come up with a publication in 1999 with the same Journal of Light Wave Technology, and they have used the material titanium indifused lithium niobate with the jet cut and bi-propagating direction. Buffer layer, they have used the silica, and operating wavelength was 1.56 micrometer. Index changes was 0.01. This index change means when we are applying the electric field across the coupling length, the total index change was 0.01. Extraordinary and extra 0.01 was the ordinary, and the 0.05 was the extraordinary. Why we are using these two words, ordinary and extraordinary? When we talk about the lithium niobate material, its refractive index actually varies in the x direction in differently and in y direction indifferently. So when we when we apply electric field across it, its refractive index changes in both the direction in different way. So one is said to be the ordinary and the other one is said to be the extraordinary. However, the driving voltage for this switch was little higher on the higher side, that is 7 volt. Then the another switch was given by some Chinese researchers and published in 2006, and they have used the thermo-optic effect on the polymers. Now the material is changed. They have used the polymers in place of the lithium niobate. Switching power is very less, 22 milliwatt, and the crosstalk is little high, minus 20 dB. Because moreover the best crosstalk seems to be around minus 40 dB, but their crosstalk was little on the higher side, minus 20 dB. Then some other authors, they have come up with the hybrid waveguide, use the polymer and silica, and they have designed the 2x2 thermo-optic switch. Then the other material which have been used, which is a combination of composite of gallium arsenide and gallium aluminum arsenide, which is also suitable to design MMI switches. Then is tapering is necessary? Do we really need to have a symmetric coupling region? Like in many of the MMI structures, this coupling region is supposed to be symmetric, but some other author had done a work with a tapered coupling region, and he has come up with the differently outcomes, and he has realized with this structure with the silica waveguides using the silicon oxynitrides. However, he has come up with the conclusion that tapering could lead to the reduction in beat length, which is a good thing. But the problem is tapering may cause increase in propagation losses, and this was published in the IEEE Photonics Technology Letters. So there were more work were done with the MMI structures, like what kind of coupling region we can choose, what could be the coupling length, what could be the coupling width, what could be the width of the input and output arms. These are very important, and if someone want to work with the MMI switches, this paper is one of the good paper, because it actually tells about what should be the width, length of the coupling region, the input output port, before if you go for design of MMI based switches. So these are the switches which have been done with within our labs, tunable MMI switches, by which we are just changing the refractive index within the coupling region. Like you can see, this is a 2x2 MMI switch. Here the coupling region, the entire coupling region is divided into two parts. One is IM1 and IM2, and just by having the different refractive index, we can actually get the switching. Similarly, this is known as the size modulated MMI switch, and this is known as the image modulated MMI switch. In image modulated switch, we are not changing the refractive index across the entire coupling region, but only at a specific point. And this point is what, let's say the power comes from here, it divides into two parts, then it recombine over here. But if by changing the refractive index of this recombined power can go up to the bar, or it can go up to the cross, just by changing the refractive index at this particular location. And you can see the table which actually tells about the refractive index relations for different regions, and they have plotted the curve in between the insertion loss and the change in the refractive index. Similarly, we can actually make them to operate for a wider optical window. That means the previous designs were working for a single wavelength only, but we can actually make them to work with the two different wavelengths. But in that case, we need to have more coupling regions with different refractive index. So we need to have a more index variation region. So in this case, we are using 4, and similarly, we can have the 2 index modulated regions, image modulated region. Then we can have the 4 also. And good thing is 4x4 MMI switch can also be make it as a switch with the uniform absolute loss uniformity. This also we have done in our lab, in which we have proved that the 4x4 switch, which can design with this particular architecture, can actually have the absolute loss uniformity. That means all the input output pattern will have the You can see how many input output pattern a 4 cross 4 will have, factorial 4, around 24. All the inputs 4, if they are connected with the all the output 4, they will have the around 24 input output connection, and we calculated the losses for all these 24 output connection and proved that they have got almost similar losses. That means this design has got the absolute loss uniformity. These are the results which actually shows how much the losses for all these 24 are varying.